Good morning, good afternoon, everyone. Welcome to this third webinar of the second edition of the YESS GAWTEC webinar series. This webinar series is focused on reactive gases. Today we have Christoph Zellweger as our speaker. He will be talking about measurement of tropospheric ozone. Before starting the presentation, I will just remind you the code of conduct. Please be polite and respectful to all the speakers and to all the participants and the speakers. I'm sorry. Please type your questions in the chat box during the presentation, and after Christoph's presentation, we will have a short Q&A, and your questions will be answered. And right now we are recording all contents in presentation, Q&A, and messages in the chat box. And the webinar will be uploaded tomorrow to the YESS YouTube channel and to GAWTEC YouTube channel as well. So now I give the floor to Sonia, who will introduce our speaker.
Yeah, welcome everyone to our webinar series. I'd like to introduce the speaker today. We have Christoph Zellweger with us. He's from EMPA. Christoph studied chemistry at the ETH in Zurich and did his PhD at the High Alpine Research Station Jungfraujoch on the topic of reactive nitrogen species in the atmosphere. Since the year 2000, he is heading the World Calibration Center for Surface Ozone, carbon monoxide, methane, and carbon dioxide. He has conducted more than 100 system and performance audits at stations of the GAW program. And he is also a member of the WMO GAW Scientific Advisory Group for Reactive Gases and the GAW expert team on atmospheric composition measurement quality and the GAW expert team on measurement uncertainty and the task group on ozone cross-section change management. His topic today is measurement of tropospheric ozone. Thank you very much for being here today, and the floor is yours.
Thank you very much, Sonia. Thank you very much, Valentina, for the invitation to give this seminar today, this webinar today. I will try to share my screen, which is always a little bit tricky because I have too many screens. But I think it soon should work. I think I have to go to presentation mode. Okay, so now you can see my screen in presentation mode, probably. Is that correct? Okay. Okay, so good morning, good afternoon, everybody. So it's a pleasure to give this webinar today. I will talk about measurements of tropospheric ozone. And let's just start with some rationale for trace gas measurements. As you all know, air pollutants and greenhouse gases emitted by human activities have a big impact on our planet. We have global issues like climate change, for example, which is mainly caused by greenhouse gases, here mainly by CO2 and methane emissions, but also ozone is a greenhouse gas, but it's not long-lived, so it's a little bit less important. But nevertheless, also ozone is a greenhouse gas. And then we have other effects where ozone plays more a role, like for example summer smog, where we can have a build-up of severe pollution events over days, especially in summer, together with photochemistry and other species like VOCs, volatile organic compounds, nitrogen oxides, etc. Also, other events like winter smog. Here, ozone is of less importance because it's mainly present when we have active photochemistry. So in the troposphere, the near ground level of ozone is mainly an air pollutant, and it threatens human health or the health of any living being and also the ecosystems. It therefore also can lead to, for example, leaf injury in plants, resulting in crop loss, and this is also important for food security. Then on the other hand, you also know that ozone is not only bad, it can also be important in the stratosphere. It plays an important role because it absorbs UV radiation from the sun. Because this composition of the atmosphere is important, we have measurement networks, like for example, the Global Atmosphere Watch Program, and also other networks, for example, on national levels. The Global Atmosphere Watch currently has 30 global stations and around 400 regional stations. And when you look here on the right side, I try to find a pointer. Okay, pointer. Here on the right side, this is just from the GAWTEC station information system. Ozone measurements, surface ozone measurements. Unfortunately, it's not very up to date because the data exchange between the data center and GAWTEC at the moment, I think it's not really working, but it gives kind of an overview, and you see that the measurements are not evenly distributed. We have many measurements in Europe. Also, if you, for example, look at this publication from the tropospheric ozone assessment report, you see that there are many measurements, especially in Europe and also in North America, where other parts of the world are less good represented, and especially there are large areas without any data, especially in Africa and Russia. As Sonja mentioned, we are running a World Calibration Center at EMPA, which is one of the central facilities of the WMO program. We do this since 1996. It already started before I was at EMPA. And we are responsible for surface ozone, but also for other species, for carbon monoxide, methane, and CO2. We also collaborate with other calibration centers, for example, for N2O, to increase the number of the audits. And as Sonja mentioned, we have done more than 100 station audits for surface ozone at global GAWTEC stations. So let's go a little bit to the history of ozone. So ozone was detected almost 200 years ago in 1839 by Christian Friedrich Schönbein, who was a professor at the University of Basel. At that time, he used this potassium iodine measurement technique, where you have paper with impregnated with potassium iodide, and that changes color when it is exposed to ozone, because elemental iodine is produced. Of course, this is not very quantitative, but he was able to detect ozone with this method. And he also detected the presence of ozone in the atmosphere a few years later. But until the 1950s, it was believed that the ozone in the troposphere is mainly from the stratosphere, from intrusion from the stratosphere, which we know nowadays is of course not true, because it's photochemically produced. I will not go into detail on how ozone is produced, but it was then linked in the 50s with the Los Angeles smoke. It was also ozone was of very high interest at the time of Schönbein, because they believed, which is probably kind of true, but I mean, it still can be used to disinfect something. They believe that this has an important role as an air purifier and eliminating some disease organism. Then another important person was Arie Hagen-Smit, who did a lot of studies on smog in the Los Angeles area. Here are some publications from the 50s when he was doing science, and he actually detected that the ozone in the troposphere is formed by photochemical reactions. So why do we measure ozone? I think we touched upon this already. It has effects on human health. It can harm lung function. It irritates the respiratory system. It can lead to premature death and illness like asthma and bronchitis, for example. It also has effects on the environment because it damages vegetation and it can lead to leaf injury, to loss of, for example, crop production. So it's important. I have this from the US EPA website, which gives a nice overview of the effects of ozone pollution. And because it is kind of harmful, it's also a regulated air pollutant, and there are threshold levels set by many countries. Here just an overview of a few of them. For example, the US EPA has an 8-hour standard of 0.07 ppm for ozone. The European Union has different threshold levels, also different units here. In the EU, it's a microgram per cubic meter. They have threshold levels, for example, for population information threshold or population warning threshold, health protection threshold. And then also Switzerland has its own standard, which is a little bit more strict compared to the European Union standard. Of course, there are many other standards in other countries, and I maybe suggest that you check the ozone threshold levels of your country. It can be interesting. So let's move to surface ozone measurement techniques. So I mentioned Schönbein, but of course, I mean, nowadays these techniques are no longer relevant. Sometimes ozone is also measured with a chemiluminescence technique. This is a reaction of ozone with, for example, ethane, and it produces ethane oxide. And it emits light, which can be detected by a photomultiplier. Also, reaction with NO is possible for the chemiluminescence method. But this technique is also it's not really widely used, especially not used for air pollution monitoring. But in some cases, it can be an advantage if you have high levels of other pollutants, for example, volatile organic compounds, which can interfere in the UV technique. And nowadays, spectroscopic techniques are most widely used, and it's mainly, I mean, really the vast majority of all the measurements that we have for surface ozone are based on UV absorption. And there are many different instruments on the market, many different brands are on the market, and they are commercially available. I will come to this in a few minutes. So the measurement principle is it's absorption of UV light. So you have, in principle, you have a measurement cell. I lost my pointer. Cannot move it anymore. Okay, well, not so important. Well, so you have a measurement cell, you have a UV source, so a light source, and then you also have to measure pressure and temperature, and you have to know the absorption coefficient. And because these, like temperature, pressure, length of the light path, that's all part of the international system of units. So in principle, it's SI traceability. And this is realized in the ozone reference instruments that we have for the UV instruments. And the ozone reference here is the NIST standard reference photometer by the National Institute of Standards and Technology from the United States. There are currently about 60 instruments worldwide. And in principle, it's a direct realization of SI traceability, because it's only measurements of the UV absorption. And when you know the absorption cross-section, your cell length. So here you have the measurement cells. Here is the light source. Here are the detectors. There is some manifold to distribute the ozone. It has an ozone generator, and then you can make different levels of ozone. So it's directly SI traceable, and well, I think the instruments exist since the early 80s. So this is Jim Norris, who still works at NIST, producing these SRP instruments with the first instrument in 1982. And we at EMPA, we have two SRPs in our laboratory. We use them for our national air pollution monitoring network and also for the GAW activities. So traceability, when you have measurements at the measurement site, they should be traceable. So this is, for example, an analyzer at any measurement station. So you need to calibrate them. Usually you do this with calibration gases. In the case of ozone, this is not really possible because ozone, as you also probably know, it's very reactive. So you cannot keep it in standard gas cylinders like you can do for many other species. For CO2, for example, for methane, it's relatively easy. They are stable over a very long time, but ozone is reactive. So you cannot have any calibration gases. So you need transfer instruments or traveling standards with traceability to an ozone reference instrument. In case of UV, this is usually an SRP. And actually the traceability chain, or in the GAW, it's organized. We have central calibration labs. And for ozone, the central calibration lab in principle is NIST, SRP number 2. And then we have where calibration centers or stations, they also have their own laboratory standards with traceability to an ozone reference. And so you can ensure traceability. But ozone is a little bit different because we have these 60 instruments worldwide, and not only one instrument. It's not only the SRP number 2 of NIST, which is the primary standard, because each of these SRPs is a direct realization of a primary standards. We have kind of 60 primary standards. And these primary standards, they are compared in the key comparisons organized by the BIPM in France. And you see this is just a screenshot I took from the latest results. Well, it's ongoing. It started in 2007. Pilot study was even earlier, and you see the results. So only national metrology institutes can participate. Also, we can participate because we are designated institute by WMO. So we represent WMO and also can participate in this key comparison. And within the uncertainty, we have agreement between all these SRPs. So it's more like the family of ozone reference instruments that define the the reference. But they have an uncertainty. And yes, you can have a look at the uncertainty budget. So there are different contributions to the overall uncertainty of the reference instruments. Uncertainty, of course, this is only the uncertainty of the reference instrument. You have to propagate this then to your measurements at the measurement sites. There are many other contributions to uncertainty, but the SRP, there are contributors like the optical path length, because you have to measure it, and there you have an uncertainty. Then you have pressure and temperature measurements, which also have an uncertainty, the ratio of intensities. But by far the most important contribution to the uncertainty is the uncertainty of the absorption cross-section. And in the standard reference photometers for ozone, since the beginning, they use a value which was published in the 1960s by Hearn et al. And this is likely it likely will be changed over the next few years, because in 2019, Joe Hodges published a recommendation of a new consensus value of the absorption cross-section at this 253.65 nanometer. This is the wavelength where we do this UV absorption measurements. And there will be a new value. It will take probably a few years from now, but the new absorption cross-section is lower compared to the one that is currently used from 1961. And this has consequences because it will change also the ozone amount fractions that are measured with SRPs and then propagated to analyzers in the field. And a lower absorption cross-section means that the ozone amount fraction will increase by about plus 1.3% with the new value. And of course, this can have implications also for the violation, for example, of threshold levels. So let's have a look at the stability of the standard reference photometers. As I mentioned, we have two of them at EMPA. One since 1993, number 15, and then we bought another one 20 years ago, number 23. And since then, we are regularly comparing them against each other. So you see here a comparison. This is the difference between the two instruments, and it gives a slope. And I just make this kind of plots. So we have here the green area. Here is the goal that we have in the goal program. So a maximum deviation of 1 ppb in the range from 0 to 100 ppb or nanomole per mole, which is the same, but the correct unit is nanomole per mole. And then I look at the bias in the middle of this amount fraction. So that's here at 50 ppb. So this point, or this comparison actually translates into this point here. So we have a positive slope and a little bit of a positive bias. And when you look at all the comparisons, you see that this SRP is very stable over time. But of course, it also changed a little bit sometimes, because in the beginning it was different. We also found out why. It was some mistake in one of the electronic boards with a wrong capacitor. So here we had clearly a bias. But since 2002, it's more or less stable, and it further improved in 2007, where there was another upgrade of the SRP systems that compensated for some systematic measurement biases due to multiple reflections in the measurement cell. So this was corrected with tilted windows that prevents the light beam from doing multiple reflections, and also better thermal insulation because there was kind of a temperature gradient over the measurement cell. And the temperature measurement was made only at one point. So the temperature gradient is now also smaller, and this gives an improved or a lower uncertainty of the temperature measurement. So here again, you see since 2007, it's really stable, and we also could confirm this by comparisons with other institutes. Sometimes we compare our SRP with NIST. We have comparisons with SRP number 0 and 2. We take part in the BIPM key comparison, and also we compare with other SRPs that we have in Switzerland, METAS, the Swiss National Meteorology Institute. They also have two SRPs, 14 and 18. And also here you see that since 2007, we have improved stability. Somehow the pointer does not really make what I want, but anyway, okay. So we have improved stability. When you look at this, it's really much smaller than the compatibility goal that we have for GAW. Then we have ozone analyzers, and here they have the same operating principle as the standard reference photometer instruments. So it's also UV absorption. It's also measurement cells. SRP has two measurement cells. Some of the ozone analyzers, they also have two measurement cells. Some have only one. I will show this later. You need reference, also a reference gas, which means just the same air, but without ozone. In the analyzers, this is achieved with ozone scrubbers or ozone converters. I will show this in more detail shortly. But let's just move for 1 minute. Let's move away from ozone, and because ozone is a little bit different, because the measurement technique over the last 30 years was always the same. It wasn't. I mean, there are a few alternatives, but I guess 99% or even more of all the ozone measurements are made with UV absorption. This has not been the case for many other parameters, like for example carbon monoxide. We have a lot of different measurement techniques there, and there was also a huge improvement in performance over the last 20 years. With a trend from slow to fast measurements, from quasi-continuous to continuous, from single to multi-species. And some of the multi-species instruments, even today, they can measure also ozone together with many other species. So there is clearly a progress can be seen, especially over the last 10 years, but also 20 years. There was huge progress, and I make some little advertisement for the next GAWTEC webinar that we have in 1 week from now. So my colleague Martin Steinbacher, he will give you some information about developments for carbon monoxide. Then we also had some developments on the low end. I mentioned this because low-cost sensors are becoming more important. There are also ozone or also low-cost sensors for ozone on the market. Unfortunately, most of these instruments, they are not really giving good results because they are relatively cheap sensors. They very often have interferences with many other components, or they are also for example, temperature dependent. So low-cost sensor is very difficult, but there is also kind of a development in. It's not only low-cost sensors, real sensors, but it's also a trend that more and more miniaturized instruments are coming on the market, and also you can find some for ozone, for example, and here there is some potential to have a good performance, because it's exactly the same measurement principle as reference, or the let's say research grade instruments, but it's just smaller. Of course, you will have more uncertainty, more noise, but in principle, it's the same technique, just very small, cheaper. So there is some potential there and some development as well. But most of the low-cost sensors are really difficult to operate, cheap to buy, difficult in interpreting the data. And I mean, you can do nice and interesting things with those sensors, but then you need to invest a lot of time, a lot of know-how, and in the end, it might not be so cheap again. So I strongly recommend that you look at, if you are interested in low-cost sensors, that you look at this report, also WMO report, where I also contributed a little bit, especially to the first version, but also to the second, which is from December last year. It gives an overview about low-cost sensors. Then, as I mentioned, for ozone, there was not much development over the past 30 years. It's UV absorption instruments. I show here instruments from Thermo, but there are many other brands as well available, and they are concerning performance. There is not really a big difference between different brands. It was not really much development. So the first instrument, for example, from Thermo, I think it was the first. It started, I don't really know when it came on the market, but until 1995 had already exactly the same operating principle as the current model that we have now. But of course, the electronics at that time was not so good. It had only analog output. So there was some progress, but not really much. And especially here from the mid-90s until now, the performance is almost the same. So there was not, compared to like other species, carbon monoxide, carbon dioxide, methane, where we have a huge development, there is not so much development in ozone. But of course, ozone is also a little bit a simple measurement technique, and the performance of these UV analyzers is good enough for what we want to do. So that's fine. So measurement principle, I mentioned it already. So there are instruments, UV absorption instruments using one measurement cell. So this is again a very old picture, or a picture of a very old instrument. I think it's no longer on the market, but you see here one measurement cell. So the principle here is you have your air inlet, then it goes to the measurement cell. You have a UV lamp, you have a detector, you measure pressure and temperature, and you calculate the ozone amount fraction with this. Of course, you need the reference, and there the air passes over this scrubber here that removes all the ozone, but otherwise it should not change the metrics. This is important because otherwise you will have interference if you change the metrics as soon as you have something which also absorbs UV light in the same spectral region. So this is relatively straightforward. I think most instruments that are currently available on the market are using this one measurement cell measurement principle, except the Thermo instruments. And I think also to GAWTEC, maybe there are others, but I don't know. They are using two measurement cells. So here is an example of thermo. There is also a model of 2B. This is a small instrument, which is cheaper compared to the other ones, but it has the same measurement principle, and it's kind of a low-cost instrument, but still gives quite good results. So here you have two measurement cells, and the air from the air inlet is split, and so one airstream goes directly to one of the measurement cells. So here you have air. My pointer does not make what I want. So here you have air with ozone, and then the other part passes over the scrubber, and in the other measurement cell you have your reference. And then you switch between the two cells. Okay, you switch between the two cells. Okay, that was too fast. You switch between the two cells, and then you have the reference in the other cell, and you make the ratios to calculate the ozone amount fraction. Also here, of course, you have to measure pressure and temperature as well. The measurement principle is exactly the same as for the SRPs, but of course the realization is not as perfect, because the cells, they are much shorter, and that's why these instruments, they can be calibrated. I will come to this later. Okay, so then there are also things that can go wrong, and when you are running a ozone analyzer in the field, usually these instruments are stable over time. They do not really need a lot of maintenance. They need some. I will come to this. But things that can go wrong are, for example, leaks in the solenoid valves. This happens very often. So normally, if everything works fine, the air is going to one of the cells. It's a little bit slow. Okay. So you have here, you have the reference, and you have the air with ozone. But in case you have a leak in one of the solenoids, then some of the, for example, of the scrubbed air can leak into the cell with the air with ozone. And then you will have a lower reading of your analyzer. And usually these leaks, they can appear very slowly. In the beginning, a very small leak. It gives only a slightly lower reading, and then it starts to increase, and it gets bigger and bigger, and it's very hard to actually realize this. So it's a little bit dangerous. Also, scrubber efficiency can be an issue, because in a normal case, a scrubber removes 100% of the ozone, and a good scrubber removes only ozone. And all other potential interference, like for example VOCs, also water vapor can be a problem, will pass through the scrubber. So this is fine, but there is also it is also possible that sometimes a scrubber degrades, and then it's only partly efficient, and you will have the same effect as with leaking solenoid valves. You will have lower ozone readings, and also here this is very difficult to detect. And for example, this is an example that shows such a bad scrubber. It's also already quite old now, but in 2003 we did an audit at the Asekrem site, core station in Algeria, and then we realized at that time something is wrong with the instrument, and we were able to identify that it was a scrubber, but then we were looking at the data, And with a statistical filter, we were able to identify the period when the problem started. So it's very difficult because you have a large natural variation of the ozone here, and then here the problem starts and it degrades, and you have lower values, and from the data alone it would be very hard to see. So it is really important to be aware of these potential problems for ozone analyzers. And in this case, for example, in ASACAM, we had to flag almost one and a half years of data as invalid, because it's also impossible to quantify the loss. You don't really know, was it 10%, 20%? That's really difficult. The same is true for if you have a leak in a solenoid. There are some tests that you can do, and I strongly recommend that you do this. I think these tests are probably available for all analyzers. I'm mainly familiar with firmware analyzers. There you can do a so-called AB ozone test. If you have a calibrator or an ozone generator, and then you produce 500 ppb of ozone, and you run this AB test. So each cell gives independent measurements, and the difference between the two cells should be less than 3%. If it's more, then there is likely that you have a problem with the solenoids, or it could also be the scrubber, but the scrubber is less likely. So what normally happens is, if something goes wrong, it's really the solenoid. Something that goes wrong that you don't realize. I mean, there are other things that can go wrong. For example, the pump. If the pump stops, but then you will see it because this gives an alarm. You have not enough flow through the instruments. The instrument will tell you not enough flow. You will check the pump. You will see it. But solenoids and scrubber is difficult to detect. So regular checks are important. I think it's whenever you can do it, and I think nowadays this should also be not a problem because you have your data acquisition systems. They usually are not like in the past where you acquired analog signals. You acquire digital signals from the instrument, and this gives you the opportunity to acquire as many instrument parameters as possible, because this can be important for diagnostics later on, like flows, temperature, pressures, intensities, etc. Also calibration settings in case you change these by accident, for example. It's important that you monitor this. Other instrument maintenance for ozone, there is not so much you have to do. Of course, you need to change inlet filters, and here again, because of the reactivity of ozone, it's important that you choose the right materials, which is also true for the whole inlet system. So Teflon can be used for the inlet filters. It's only Teflon. For the inlet system, it can be also other materials, but it must be inert, and it must be something that does not destroy ozone. So either the way on how it is realized, or contact with surfaces should be minimized. If there are contacts with surfaces, then it has to be like Teflon or glass, and no other materials, because then you have a chance that you lose ozone. Of course, this can also be cleaned, also the measurement cells. I also would be, when you protect the instrument with filters, then I think cleaning of measurement cells is, you can do it, but you should also be careful that you don't do it too much, too often, sorry, because sometimes it's not really necessary. And if you, like, for example, if you service the instrument like every 2 years, and you are running it in a relative, depends also where you run it. If it's a heavily polluted site, then maybe it should be done more often, but otherwise just do it as required. Okay, so we have these analyzers, and they need to be calibrated. Usually, and I think all the instruments on the market, they have the ozone analyzers, they have adjustable calibration settings. Usually it's span or background and offset, offset or background or span or slope, sometimes it is called. And you can adjust this when you compare them against reference instrument, which can be either directly an SRP. This is in most cases not the case because you don't really have an SRP available, but sometimes some institutes maybe have. Others, they can use an ozone calibrator, a laboratory standard, a transfer standard with traceability to an SRP, and then compare with the ozone analyzers. And then you have in principle 2 options. You can adjust the calibration settings in a way that you have a perfect match, or almost a perfect match, as good as you can do. Or you can also apply post correction to the data because you know the relationship, you know the bias, slope and intercept, and you can correct it afterwards. So there are 2 possibilities, but once it is calibrated, then I recommend that you don't really change the settings too often. If they change, if you have one calibration and half a year later the next calibration frequency, yes, it's because it's relatively stable. It's not, ozone instruments are usually not drifting away. So calibration frequency is, you don't have to do it too often. So every 3 months, for example, is already quite often. Every half year, or maybe depending if you are in a region where you have a very distinct seasonal cycle of ozone, then maybe you want to do it to cover all these seasons. But if you see changes which are large, then most likely something is wrong with the analyzer. So be careful, don't just adjust the settings, because if they change significantly, this is usually some kind of indication that something is wrong with the analyzer or the calibrator, but this has to be checked. So to do ozone calibration, you need zero error, and there are certain requirements for the zero error. So it has to be dry. There is a standard for this, a DIN standard, 14626 from 2012, the last edition. Requirements regarding water vapor. It also has to be, of course, free of ozone and other interfering compounds such as toluene and xylene, for example, which can cause interference. So the zero error has relatively strict requirements that you use for these ozone calibrations. I will show now some traveling standard comparisons. So we are using instruments, calibrators, ozone calibrators in the field to calibrate ozone analyzers. And for example, for the GAW audits that I do, there we really have to make sure that the traceability chain is as short as possible. So I compare my traveling standard against one of my standard reference photometers before I go to the field. So these are the orange points here, and then I do the field measurements and I come back and compare it again. And this is usually 3-4 months later when I go to a GAW station because it's shipping. There are some parallel measurements at the GAW station, so it takes quite some time. And you see this is really stable. It's not really changing very much. And also the comparison between traveling standards and SRP, they are well within half of the data quality objective that we have for ozone measurements in the GAW program. So now in this graph I show the results of the ozone audits that we did over the last 25 years. So this is more than 100 individual comparisons for different instruments. Here again, you have the goal that we have in GAW. And of course, not all the instruments in the field are meeting this goal. It's maybe roughly, well, I would have to look because there are many points here in the middle, but it's a little bit more of, I think, yeah, a little bit more than half of the instruments that meet these requirements. And what you also see, these are different brands. Well, in the beginning, there were some old instruments in the 90s and early 2000 until 2005, but most of them are now replaced. Monitor Labs at that time and the CB, also thermo instruments 49, model 49. They were not as good as the instruments that we have nowadays, but I mean, you see even other brands and performance is very, very similar. So there is kind of an improvement over time, but still, I mean, it's relatively difficult to reach this one ppb or 1 nanomole per mole goal that we have in GAW. Yes, yeah, it's 56% of the instruments so far. When you look at all the comparisons within the goal, if you look only at the 49C and 49I, it's 61. But I think it's not because it's thermo instruments; it's because we don't have these old instruments in these comparisons. So also other brands, they will perform similar compared to the thermo instruments. So these are the stations that we have audited already, many of them several times. So this brings me almost to the end of my presentation, but I want to mention a few more things. So successful measurements of air quality with good data quality needs not only know-how, not only instruments, it also needs sufficient funding and an adequate infrastructure. So you cannot just buy an ozone analyzer, switch it on, and then measure ozone and then think that's it. No, you need sufficient funding. You need funding for maintenance. Because instruments, they can break down. So it's actually much more expensive. And especially in case of ozone, you also need adequate infrastructure. For example, a adequate inlet system where you don't have a loss of ozone in the inlet system, because this is really also one of the things that can go wrong because ozone is so reactive. You need not only the instrument, you need some calibration facilities, or you have access to an ozone standard, for example. You need data acquisition system, and so on. You also need, if you want to do measurements, for example, in the GAW program, you need long-term commitment. Here a good example here in Galbally at the GAW station Cape Grim. He worked with ozone for decades, I think. Really long-term commitment also of the institute performing such measurements is needed. You need educated staff and enough staff. Here also a good example I found ISANIA staff. Enough staff, educated staff is important. You need clear responsibilities and also knowledge sharing, because operators sometimes leave or there are different people responsible for measurements, so knowledge needs to be shared. You need collaboration with national and international partners. This is all very important. And last but not least, also an efficient administration. And this is sometimes you cannot really influence this, but the administration, for example, if bureaucracy is different in different parts of the world, and our experience is that in some places it's more difficult, and then it's also difficult to react. For example, if you have an instrument that breaks down, you must be able to act immediately to solve the problem, because otherwise you will have data loss. And well, the last thing I'd like to show is there is a guideline for the continuous measurements of tropospheric ozone. It's the GAW report 209, which was published in 2013. I recommend that you look at this report. I think it's still up to date, because ozone has not really, or the measurement of ozone, it has not really changed very much over the last 2 decades. So this report is up to date. The only thing that will change for sure in the near future is the absorption cross-section. I think then these reports, together with many other standards like ISO documents that deal with ozone, they need to be revised, and new versions should come out. So with this, I would like to come to the end, and I would like to thank you for your attention, and also would like to thank Meteo Swiss for the support of the GO activities at EMPA, and also, of course, the staff at various GO stations for their support during the audits. So thank you very much.
Thank you, Christoph, for your very detailed and interesting presentation. I'd like to start the question and answer session now. We have collected some questions in the chat box, and I will read the first one. It says, which is the more correct designation for the current method, spectroscopy or UV photometry?
I think UV photometry is a little bit more specific, because you say already what you are doing. It's UV photometry. That's correct. And I think this is a kind of a spectroscopic technique, and there are other spectroscopic techniques, but UV photometry, yes, that's correct, and probably more specific.
All right, thanks, Christoph, for a great talk. I'll ask the second question. We have a couple from Orlando, but I think the first one was answered, so I'll skip to the second. How long is the average lifetime of ozone analyzers?
The lifetime of ozone analyzers is quite long, especially when you compare it to other instruments for other species. Part of it is because for other species, for example, for carbon monoxide, it's not only the lifetime, but it's also the progress that is made. You probably want to change to a new analyzer, not because your analyzer is not working any longer, but because there are better instruments on the market, and this is not the case for ozone. So the lifetime is quite long. It of course depends on how well you maintain it. The measurement principle is also not so complicated, and it's also relatively easy to repair an ozone analyzer. I mentioned, for example, this leaky solenoids. If you have such a case, then you can replace it. After this, it will work again for years. It's a little bit difficult to say, because especially the solenoids, they can break within 2 years, or they can last for 20 years. It's very difficult to predict, but the lifetime is at least, I would say, like something like 10 years. Or
Right,
longer.
Sorry. Sorry, Christoph. The next question is from Sama Aldabad. She says, thanks for the valuable information. How to join the global network of ozone monitoring?
So that's a difficult question. So how to join the global network of ozone monitoring? Well, if you are running a station, and if you are interested in becoming part of GAW, then I think you can apply for this at WMO. I think you have to show that you are already successfully running it for a certain time. In the beginning, it most likely will be kind of a local or regional station. You can apply for this. I think there are some requirements, especially regarding long-term commitment that you have to fulfill. But in principle, you can apply for it with WMO, and probably Claudia could answer this question better than I. Yeah, but it's a process that you can approach WMO.
Thank you, Christoph. Yeah, I will post the link where the procedure is explained, but it's pretty much as you said, so thank you. The next question is, it could be said that low-cost sensors would only serve for specific studies, but not for continuous monitoring.
Yes. I think for continuous monitoring, especially if it's like legal monitoring, low-cost sensors they cannot be used because the data quality there is certainly not good enough. But I mean, they can be used for different campaigns. For example, if you are just interested in differences between sites, for example, but you have to be careful, because when you use low-cost sensors, they and you, let's say you buy 100 and you distribute them in a city, then it's difficult to compare them, because each of them, it probably behaves different than the other one, and so it's really difficult. I think low-cost sensors, they can be used, especially if you use them in addition to some existing measurement network, where you have the possibility to link measurements or to kind of reference instruments, because otherwise it might be difficult. It also depends on the sensor, because there are in the field of low-cost sensors, there's a huge variety and also a huge difference between performance of individual sensors. Some of them are better, some of them are not good at all. They just give absolutely wrong numbers, and this is relatively difficult. I mean, sometimes you see it straight away, but not always, because it's not easy to see if a number can be correct or wrong in some cases. So they can be used, and I think the guideline or this recommendation document, the WMO report 1215, gives some examples where low-cost sensors can make sense, and also low cost very often does not really mean low cost. when you want to have something useful in the end with the data, because then you need to invest much more into data analysis compared to like normal ozone analyzers, or I mean, this is true for probably any other species as well.
Thanks for that. There's some very good points in there. I'll jump in with the last question. Well, it's from me. I'm curious if it's possible to, and if there's interest in reprocessing older data with the new ozone absorption cross-section that you mentioned.
Yes, this should not be very complicated. So the absorption cross-section will change, and in the SRP, and I think most of the UV instruments, they were, or at least they should have been calibrated against an SRP instrument. So there it was one absorption cross-section that was used from Hearn published in 1961, and the new absorption cross-section is by 1.29% lower compared to the Hearn value. So in principle, it's just a factor. It's easy to reprocess the data because it's only a factor. I think it's very important that you also report when you, for example, when you submit data to the World Data Center for reactive gases or to any other database having ozone data, it's very important that you specify the ozone absorption cross-section in the metadata. This, until now, unfortunately, was not always the case. So if you look at data, for example, available from World Data Center for reactive gases, then you very often see when you look at the measurement method, you see only UV absorption, but that's not the whole story, because the whole story is it's UV absorption, and we used the absorption cross section from Hearn in 1990 from 1961, and then it's clear. And so the new value, the new consensus value that will, well, there is currently a task group working on this, and I'm a member of this task group as well. So there was an initial timeline to change this for the year 2024, but I think this will be a little bit too challenging. So it probably will be a little bit later then, because some of the standard documents have to be changed, like some ISO standards, for example. And this process usually takes quite some time. But it's conversion between the two absorption cross sections should be easy.
Okay, so I think we have no more questions. Thank you again, Christoph, for being here today and doing this presentation. I would think we will close the webinar now. We will also would also like to advertise our next webinar. Martin Steinbacher will speak at the 4th of November. This is next Thursday. His topic is measurement techniques of carbon monoxide in the atmosphere. We posted the link in the chat box. I hope to see you next week and wish you a pleasant week.